Okay, so let's get started. Good morning, good afternoon, and good evening to all our customers joining us from across the globe. Hello, everyone. My name is Lokesh Chara, and I'm the Senior Manager for the Arista Technical Services team. And on behalf of the entire team, I extend a warm welcome to each and every one of you to this remarkable webinar series graciously hosted by the Arista TAC team. For our customers who are joining us for the very first time or maybe joining us after a break, I'll quickly cover a few details about this initiative. Mansi, let's move on to the next slide, please. Our aim with these webinar sessions is to work on sharing the knowledge that we cultivate here in the TAC world with our customers and cover topics in depth which are most useful and applicable to all our customers. Recording of all our previous sessions in 2022 and 2023, including presentation material and question and answers, are available on our Arista community page if you'd like to review it. Starting in 2024, we are actually bringing more Arista products into our webinar in the technology mix, and we are doing a deep dive into how these products together can offer a helpful platform for debugging any common networking problem. This is our second session this year, and we have scheduled out for our next session as well as for the Q2 series as well. Coming to today's session, we are going to do a deep dive into the traffic blackholing issues that can occur in any network. And we are going to cover some use cases that we see in our TAC interaction and common problems that we come across. We'll also go through the debugging steps which can be applied to any such issues and to troubleshoot these problems and the EOS CLI tools that will come handy in such situation. So for today's session, we have our subject matter expert, Mansi Joshi, who will be walking us through these debug scenarios. Mansi will take us through some lab scenarios that we have encountered in our tax interactions. And for everyone's reference, we have prepared a lab topology diagram, and we already sent it out to our registered customers earlier last week. Mansi will be highlighting this topology in between the debug scenarios, but it'll be a good idea to kind of take a snapshot of this topology and keep it up on your screen for your reference. We have a PDF download link available in the QA section, which our panelists are putting right now. Thank you, Meetu. And so I request all our customers to please download it and keep it handy during the course of the presentation. Along with Mansi, we also have our technical leads as part of the panel who can help answer any question that you may have during the course of this presentation. You can use the Q&A manager to ask our panelists any questions during the course. And before we deep dive into the troubleshooting scenarios, I quickly would like to highlight our new product offering, that is the TAC custom training. So Mansi, let's move on to the next slide, please. Based on the valued feedback that we've been receiving from a lot of you and just a wider interest in the personalized custom trainings, we have kickstarted this effort, which is essentially a fully customized training session led by our TAC experts. We customize the content of these sessions based on the feature set, platforms, designs that you have in your network environment. And we also include our comprehensive analysis of the recent TAC cases as part of these sessions in order to provide you a complete picture of your network and the problems that you've been experiencing in your network. It also includes the key recommendations from our TAC experts to overcome these problems in order to avoid outages. So these sessions are delivered in the form of the debugging scenarios to ensure readiness of your network operations to handle such challenges. And since we started this offering, we have delivered many such sessions to our cloud titans and enterprise customers, and we continue to receive great feedback on quality as well as the content. This is a paid offering, and if you are interested in scoping a session with us or just interested in learning more about this offering, please do reach out to us on tac-custom-training@arista.com. So without taking any further time, I'll hand it off to Mansi for taking you through the presentation. Mansi, take it away.
Thank you, Lokesh. Hello, everyone, and welcome to the second session of the 2024 webinar series. My name is Manasi Joshi, and I'm a part of the Arista TAC team. Today, we'll be talking about how to troubleshoot traffic blackholing in a network. In the previous webinar, we saw how to approach latency in a production fabric, from tracking down which device might be introducing it to what actions we can take to fix the issue. And in today's session, we will look at traffic blackholing or traffic loss, which is also a pretty common problem that can be seen in networks. The symptoms of this issue can be a bit vague to begin with, so it can be challenging to figure out which device to focus on or where exactly to start the debugging. In this session, we will see how we can use different tools to effectively troubleshoot this issue. So let's get started and take a look at the scenario that we have. Our network layout consists of a fabric spread across two sites, data center 1 and data center 2. In both the sites, we have a leaf spine topology. The application hosts are connected to the leaf switches, which are completely layer 2 devices. All the routing is being done solely on the spine devices. The DC1 spine switches have shared gateways configured for the VLANs local to DC1, and the DC2 spines are gateways for the VLANs local to DC2. We have two links going between the sites, with the link between the spine 1 devices forming the primary path and the link between the spine 2 devices forming the secondary path. Both these intersite links have eBGP configured across them. The spine 1 devices form one eBGP neighborship, and the spine 2 devices form the second eBGP neighborship. For routing within the data center, we have iBGP and OSPF configured between the spine 1 and spine 2 devices in each site. The host subnets 172.22.10.0, 20.0, and 30.0 are local to data center 1, and 172.22, 40.0, and 50.0 subnets are local to data center 2. All the host traffic is part of the VRF intranet. And we also have all the switches in our fabric streaming telemetry data to CloudVision. Now, during a steady state, when both the links are up, we expect to utilize only the primary path for any intersite data transfer, which is the link between the spine 1 devices in both the sites. This is achieved by assigning a higher local preference to the eBGP neighbors on the spine 1 devices so that this route is always preferred. During this time, on the spine 2 device, the routes learned for any remote subnets are IGP routes pointing to the spine 1 device in that site. So any host traffic hashing onto spine 2 during this time will be forwarded to spine 1 and then be routed out of the site from spine 1. In the event that the primary link goes down, the intersite routing now shifts to the spine 2 devices. Any traffic hashing to the spine 1 device during this time will be forwarded to spine 2 and then be routed out of the site from spine 2. In this way, we expect to have a failover path in place where even if the primary link goes down, the application traffic does not get affected. Now, let's take primary link between the sites went down. After this, ideally, we would have expected the second we started seeing some retransmits in the network for TCP flows. The network reachability scripts running on some of the hosts also started reporting random timeouts. The impact was intermittent, and because of this, the customer was not able to pinpoint the problematic flows with certainty. So one of the asks was also to help them figure out how widespread this problem actually was. Now, this issue can actually be split into two parts. To begin with, we need to narrow down the scope of impact and identify at least one of the broken flows as a starting point. And then we need to actually pin down the problem and make any necessary changes to fix the issue and restore the traffic between the sites. Let's first think about how we can identify at least one flow as an impacted flow for us to focus on. According to the customer, the host-to-host traffic is still active, but unfortunately, we don't have access to the hosts, so we can't log into the nodes and examine this traffic. The issue is also intermittent, which means that we cannot focus on a single snapshot at one instance of time, but rather we need something a bit more comprehensive. A network observability tool or a flow monitoring system like NetFlow or IPFix collectors can be useful in this case. While there are various NetFlow collectors that can potentially be used here, in today's scenario, we will be working with the Arista Analytics node. This tool can give us substantial visibility into the network in terms of the flows, the IPs, the traffic rates, and so on. So let's see how the analytics node can help us here. We briefly discussed about the DANZ monitoring fabric during our first webinar. This is a fabric of switches separate from the production fabric, which receives a copy of the production traffic and forwards it to special function nodes for additional processing and analysis. We looked at the packet recorder node during the previous webinar, which receives and stores a copy of the data from the production traffic. Another special function node is the analytics node, which receives the processed records of data streams and can provide visualizations through an extensive UI for complete traffic visibility. Let's first see how the analytics node actually gets the data from the production network. We have span sessions configured on all our production devices, which are constantly sending copies of the packets towards the DANZ monitoring fabric. The DMF switches then deliver these packets to the service node for any additional processing, like header stripping or deduplication. One such operation that we perform on the data is to convert the data stream into NetFlow records. These records are then delivered to the analytics node. Along with this, we also send certain packet metadata, like the device information or the interface where the packet came in to the analytics node. The analytics node can then integrate the metadata and the NetFlow information to give us a complete picture of the traffic flows in the network. It also has configurable timeframes, so we can look at the data from before and during the issue state and do a comparative analysis to see if we can spot any kind of patterns. So let's log into the analytics node and check what we can find. So here we are on the analytics GUI. And as you can see, we have various dashboards available here for complete traffic visibility. Let's check out the NetFlow dashboard first, since the data from the production network is coming here as NetFlow records. We can see the various flows here visualized as per the source and the destination IPs, and we also see the comparative traffic distribution for these flows. These IPs correspond to the host subnets that the customer provided. So over here, we have a top talkers table on this dashboard. Let's check out this data. This tracks the flows with the maximum throughput over a given period of time. We know that the primary link went down around 10 a.m. So this time frame that we have set over here is the 30-minute time frame before the issue started. And this is essentially the traffic during the steady state. Some of the top talkers from during this time are listed below. We can see that the flow from 172.20 to 20.10 to 40.10 seems to be having the maximum throughput during this time. Now, let's check the same data, but during the issue state, in the half an hour after the link went down. So we will change this time frame from 9:30 to 10 to 10 to 10:30, which gives us the 30-minute window after the issue started. After updating, what we can immediately see is that there has been a substantial decrease in the amount of traffic for the 20.10 to 40.10 flow. The total throughput is now almost 1/5 of what it originally was. Though there are some changes in the traffic rates for the other flows as well, none of them are as drastic as we can see for this 20.10 to 40.10 flow. So it's a good bet that this flow from 20.10 to 40.10 is an impacted flow and would be a good starting point for us. So from the analytics node, we were able to confirm that certain flows are working fine even after the primary link went down. These are the flows for which the traffic rates did not change much after we changed the time window on the NetFlow dashboard. And then we were also able to narrow down a problematic flow to focus on, which is the 172.22.20.10 to 172.22.40.10. This is essentially the flow from host 2 in data center 1 to host 4 in data center 2. Now, one question that is raised here is that if all the traffic is going from one side to the other over the same secondary link once the primary link goes down, then how come some flows are working fine while others are seeing an intermittent impact? So let's see how we can go ahead from this point. Generally, once we narrow down an impacted source and destination IP, the next step might be to quickly try a ping test or try a trace route to see at which hop it fails. But here, we can't log into the hosts, so we cannot use these options. We might also think of taking a packet capture to check the packet headers for the impacted flow, but we haven't been able to isolate any single device as a point of failure yet. So we don't really know where to start taking the captures. There's also the fact that we have fairly high rates of application traffic running over a single link between the sites. So it's possible that we just end up missing the packets we are interested in. Now, one of the reported symptoms of the impact was that the network reachability scripts on the hosts are seeing intermittent timeouts. We checked with the customer on what these scripts are doing, and we found out that they are basically sending out ICMP packets periodically towards the end destinations to check reachability. We can't check what error messages these scripts are failing with because we don't have access to the hosts. But if we could just analyze that background ICMP traffic, more specifically, if we could analyze any errors that are seen in those ICMP flows, then that might give us more hints about why the failures are happening. The analytics node has a specialized dashboard for ICMP traffic, which we can use in this case. So let's go to the analytics node again and take a look at the ICMP dashboard to see what further information we can get. So here we are on the ICMP dashboard for ping traffic analysis. It gets the metadata for the ICMP flows from the DMF filter switches and uses this to provide a visualization of the flows. We can see the IPs corresponding to the host subnets are already populated here, which is coming from the reachability scripts running on the hosts. From the NetFlow dashboard, we were able to narrow down 172.22.20.10 to 40.10 as an impacted flow. So we can use these IPs as filters to try and get more specific information, which is relevant only to the problematic flow. So we're adding these IPs as filters over here. And now after updating, these are now the statistics related only to these two IPs. If we take a look at the ICMP errors data over here, we can see some TTL expired in transit messages being generated. Let's filter further for these errors specifically. We can do that by clicking on this section. We can see that the message source for these errors is 172.22.20.2, which is seen in the top leftmost panel, and the destination is 20.10, which is seen from the top rightmost panel. This 20.2 IP is the gateway for the 20.0 subnet and is present on the DC1 spine 1 device in data center 1. So based on this, it seems that DC1 spine 1 is generating TTL expired messages. We have now found two important points from the analytics dashboards. One, we are fairly certain that the flow from 172.22.20.10 to 40.10 is one of the impacted flows. So we now have a problematic flow to focus on. And two, we also learned that one device in the network, the DC1 spine 1 device, is generating TTL expired messages and sending it back towards the host. Now, TTL expired messages are generally seen when traffic ping-pongs between the same next hops until the TTL times out. This could indicate some kind of a loop in the network. But it's still not completely clear to us how a loop is getting created with only a single link active between the sites. And why does it happen only after the primary link goes down? But since we are suspecting a loop, as the next steps, it would be a good idea to check the routing tables on the switches during the issue state. So let's log on to the device's CLI now. We saw that the TTL expired messages were being generated from DC1 spine 1. So let's first check the routing table on this device. We are already in the VRF intranet, which is the VRF being used for the host traffic. And checking the route for the 40.10 IP, we see that this route is being learned via OSPF, and the next hop for this device to reach this subnet is DC1 spine 2, which is expected. Now, let's check the same output on the spine 2 device. Running the show IP route command for the IP 172.22.40.10, which is the host 4 IP, this output also looks to be as expected. The spine 2 device is learning the route for this subnet via eBGP from DC2 spine 2, which is populated as the next hop. Coming to the devices in data center 2, let's also validate the routes on these devices. We will first check the route on DC2 spine 2 for the host 4 IP 40.10. We can see that this subnet is showing as directly connected, which is right, because this subnet is local to data center 2. The forward path looks okay then, but maybe there's something wrong with the reverse path? Maybe the routing is failing when we try to reach the 172.22.20.0 subnet from data center 2. So let's also check the reverse routing path on this DC2 spine 2 device, and let's check the IP route output for the host 2 IP, which is 172.22.20.10. This output also looks to be as expected. The 172.22.20.0 subnet is local to data center 1. So on the data center 2 devices, it is learned as an eBGP route, with the next hop being DC1 spine 2 device. We have now checked the routing tables on the devices for both the forward and the reverse paths, and we did not see any discrepancies as such with the next hops. All the next hops do seem to be populated correctly. So if the routes are correct on all the devices, then where exactly is the traffic failing? And why do we have TTL expired messages in the network if we did not see any sign of a loop yet. So we know that the issue has been intermittent. One possibility here is that the routes might be flapping, and we just happened to run the command when the correct states were populated in the routing table. So instead of relying on a single snapshot, we now need a tool which monitors the device states continuously so that we can review the data over a period of time for any signs of a route churn on the devices. As you might have guessed, we will now be using Cloud Vision to get a more comprehensive look at the routing tables on the devices. So let's log on to Cloud Vision now. Here we are on the Cloud Vision GUI, and we can see that all the devices from both our data centers are added to Cloud Vision and are actively streaming data. Let's first check the data from the Spine 1 device in Data Center 1. Going to the routing table information for this device, we know that the primary link went down around 10 a.m. So that's the time frame that we have currently set here. And as you can see, there is definitely some kind of churn going on in the routing table for this device, where the route for the 172.22.40.0 subnet is constantly being modified, removed, and re-added. We can see that this churn is happening every few seconds, and particularly for this one subnet. Let's move to the routing table on the DC1 Spine 2 device and check if we observe a similar pattern there. Going to the DC1 Spine 2 and to the routing table information, here also we see that there is a route churn for that same subnet 172.22.40.0. Let's switch to a live view to monitor the current states in the routing table. Going down to the actual routing table output, and over here, we can see that the route for this subnet is flapping between eBGP and iBGP, alternately pointing to DC2 Spine 2 and DC1 Spine 1 as the next hop. We are now back on the device's CLI, and let's see if we can validate the findings from Cloud Vision via switch CLI as well. We have a utility on the switches called the watch command, which will run the command output periodically every 2 seconds, so we can monitor for any changes in the output. Let's try to run a watch command on the show IP route output on these devices. And let's see if we can spot the same churn that we saw in CVP. Running a watch command on the show IP route for the 172.22.40.0 subnet. And then let's also run the same command on the Spine 2 device for the 172.22.40.0 subnet, which is the one that we saw from CVP as the subnet seeing the route churn. And with the watch command, we can now clearly see that the routes are flapping on both the devices. We missed it initially when we ran the show IP route command just a single time. On the Spine 2 switch, we alternately see an eBGP route with the next hop as DC2 Spine 2 expected, and an iBGP route with the next hop as DC1 Spine 1, which is not expected. So there are instances on the Spine 2 device when the route wrongly points to DC1 Spine 1 as the next hop. The route on DC1 Spine 1 is also flapping between iBGP and OSPF, but in both cases, the next hop for DC1 Spine 1 remains DC1 Spine 2. We have now confirmed the presence of a loop in our network, which is created when both the devices point to each other as the next hop. When this happens, the host traffic will keep looping between the spine switches in DC1 until the TTL times out. To see how this loop is actually getting created, let's see how the routing has been set up. So we'll first check the BGP and the OSPF configs on DC1 Spine 1. And here's the OSPF config. From the BGP configs, the first thing that we can see is that the local preference on spine 1 for the eBGP neighbor is set to 150. Since this is the primary link, we always want to prefer this path during a steady state. And that's why the local preference for this neighbor is set to a higher value. We can also see that we are redistributing OSPF into BGP and BGP back into OSPF using route maps. Let's now check what these route maps are and see how the redistribution has been configured. First, let's check the route map, which is redistributing the BGP routes into OSPF, which is the route map BGP to OSPF. And then here's the second route map, which is doing the redistribution from OSPF to BGP. Both these route maps are matching on a prefix list called DC internal. So let's check out this prefix list. Okay, so this prefix list is allowing the 172.22.40.0 subnet to be redistributed. Essentially, we are redistributing one particular subnet from BGP into OSPF and from OSPF back into BGP. And this mutual redistribution without any filtering is what is causing our loop. This also answers the question of why only certain flows are getting affected. We have applied a prefix list here, which allows for the redistribution of only the 40.0 subnet. So only the traffic to or from this subnet will be affected. Let's now see in more detail how the routing loop is actually getting created. The 172.22.40.0 subnet is advertised from the spine devices in data center 2 via eBGP. When the primary link goes down, the secondary path becomes active, and DC1 spine 2 learns the 40.0 subnet as an eBGP route, with the next hop being the DC2 spine 2 device. This eBGP route now gets redistributed into OSPF and is learned on the DC1 spine 1 switch as an OSPF E2 route. Because we have mutual redistribution of routes configured, DC1 spine 1 redistributes the OSPF route back into BGP and advertises it towards spine 2. This causes a route flap on the spine 2 switch, where the 40.0 subnet now gets learned as an iBGP route, with the next hop being DC1 spine 1. The cycle repeats from here, and we see that the routes continue to flap on both the devices, with both devices at times pointing to each other as the next hop. And that's basically what's creating our loop over here. When the primary link is up, because we have a local preference of 150 configured for this path, the eBGP route always wins on the spine 1 device. So we essentially avoid the eBGP to iBGP flap, which is what is triggering the mutual redistribution loop during our problem scenario. And that's why we do not see the issue when the primary link is up, and we only see it after the secondary link becomes active. Now that we understand how the loop is being formed, let's talk about how we can prevent it. We essentially want to set up the devices in such a way that spine 1 does not redistribute the OSPF route that it learned from spine 2 back into BGP, and it does not advertise itself to spine 2 as the next hop for that subnet. One way to do this would be by using route tags. Route tags are arbitrary 32-bit numbers which add an additional attribute to the route being redistributed into a protocol. So for our scenario, we can set the route tags on the prefixes redistributed from BGP into OSPF on the spine devices. And then we can use these tags as a filter on the other device and block these routes from going back into BGP. So let's see how we can implement the route tag solution to resolve this issue. First, we will add a route tag on the routes being redistributed from BGP into OSPF. Let's see the route map in question, which is BGP to OSPF. If we check the current configuration for this route map, right now we are only matching for the prefix list DC internal. Along with this, let's add a clause here to set the route tag to some number. Let's say I'm setting the tag to 20. After this, we will make a change to the second route map, which is used for redistributing from OSPF into BGP. And we will use the route tag 20 that we have just set to block the prefix from going back into BGP. So for the second route map, which is OSPF to BGP, we will add a deny statement here, and we will match for the deny statement on the route tag 20. Now, if we see the complete configuration for this route map OSPF to BGP, with the first statement, we are denying the routes matching the tag 20 from being redistributed into BGP. And with the second statement, we are permitting any other routes matching this prefix list, which do not have the tag, to be redistributed. Let's also add the same configs on the second spine device, which is DC1 spine 2. Firstly, we will add a tag to the route map used for redistributing from BGP into OSPF. We are again setting the tag to 20. And then we will add a deny statement to the second route map, which is used for redistributing from OSPF into BGP. So for the route map OSPF to BGP, adding a deny statement which matches on the tag 20. Now that we have made the changes on both the devices, let's see if the routing table has stabilized. So let's once again run a watch command on the show IP route output for the 172.22.40.0 subnet. We will do this first on the DC1 spine 1 device. And along with this, let's also run the watch command on the DC1 spine 2 device for the same 172.22.40.0 subnet. And now this output looks much better than before. The routes are not flapping anymore, and we can see that they are remaining steady. On the DC1 spine 1 device, the next hop is being learned as DC1 spine 2, and on the DC1 spine 2 device, the next hop is being learned as DC2 spine 2, which is the expected behavior that we wanted to achieve. So based on the routing table output, it looks like we managed to fix the issue. Let's also validate that from the analytics dashboards. So we are back on the analytics dashboard, and the time frame that we have set here is the last 5 minutes, which is when the configuration change was made to resolve the issue. Let's check the top talkers table on the NetFlow dashboard one more time. Here we can already see that for the 20.10 to the 40.10 flow, which was our impacted flow, the traffic has started to recover, and this flow has again become the #1 top talker in the network. The total throughput of the data that we see here is lesser than what it previously was because we have a much smaller time frame set now. Along with this, let's also check the ICMP dashboard and verify that the TTL expired messages have also resolved. Even in this case, for the 20.10 to the 40.10 flow, which we have applied as filter, we are now no longer seeing any TTL expired messages in the ICMP errors. We only see the echo requests and the echo replies, which the network reachability scripts are sending for establishing reachability. So even from the checks on the analytics node, it looks like we have been able to fix the issue and the traffic is now starting to stabilize. And this concludes our troubleshooting demo for today. So let's go back to the slides for a quick review of today's discussion. We started out today with a kind of a vague problem statement of intermittent impact to multiple traffic flows when the primary link went down. We were not sure of the scope of impact initially, and we didn't even have a sample impacted flow to begin with, which made troubleshooting a little challenging. Using the Arista analytics node, we were able to analyze the traffic patterns, though we did not have access to the hosts, and we were able to find one impacted flow, which we used as a sample flow to focus on. As an extra data point, we also saw that one device in the network was generating TTL expired messages, which sort of gave us a hint that we could be looking at a loop in our network. Next, using Cloud Vision, we validated that there was a routing churn happening on the DC1 spine devices. We checked the routing table flaps and found that there are instances where both the devices point to each other as the next hop, which confirmed the presence of a loop in our network. Using the switch CLI, we checked the configuration on the devices and saw that we are redistributing OSPF into BGP and BGP back into OSPF without any filtering, which was what was creating our loop. To correct this, we set the route tags on the routes being redistributed from BGP to OSPF. And then we used a route map to block the routes with tags from going back into BGP. Once this solution was applied, we saw that the routing table on both the devices had stabilized, and the traffic also started to recover as we were able to confirm from the analytics node's dashboards. So that's about all we have today on how to go about troubleshooting traffic blackholing. Thanks for joining in today, and I hope you found this discussion to be useful. With that, I will now hand it back to Lokesh.
Thank you, Mansi. Let's move on to the next slide, please. Thank you for covering this topic in detail, Mansi. Really great technical stuff here, and we sincerely hope that this session was useful for everyone. Again, the recording of this session along with the previous sessions will be available on our Arista community page, which will include the presentation reference material, questions that we covered as part of the webinar. But along with these materials, I want to emphasize that there are a number of good articles that we have available on our Arista community page, which can be helpful for various other topics. So I definitely would recommend everyone to leverage that knowledge base and visit the Arista community for these articles. Our next session in this Q1 series is scheduled for the March 27th at 11 a.m. Eastern or 8 a.m. Pacific. We highly recommend everyone to attend that as well. And also the schedule for the Q2 series is out, so you don't have to re-register. The same registration link what you have that will allow you to attend all the upcoming sessions as well. Taking a cue from the technical deep dive that we just went through, if you're interested in scoping a custom training session with us or just interested in learning more about the TAC custom trainings, please do reach out to us on tac-custom-training@arista.com. Our moderators have also put in the feedback form, short feedback form with 3 to 4 questions in the chat. So I request everyone to provide your valuable feedback using that Google form link, as we definitely intend to use it for our future sessions. And now I'm going to keep the webinar open to wrap up on the question-answer questions and what you have at this point. So you can use the Q&A manager to ask our panelists any question at this point. There's a question around, can any RSS switch be integrated in the DMF fabric? So with the latest DMF release, that is 8.5, the support for the US platform expands up to like 50 plus platforms at this point. So you have a wide variety of platforms to pick and choose from, and the support goes from 10 25 and 40 or even like 100 and 400 gigs at this point. So you can pick and choose from all the like wide variety of platforms that we have available as part of the DMF fabric. So I think there's just one question remaining from Ron. Vignesh, do you want to take this question, please?
Yes.
Thanks.
So the question was about whether we can use S-flow records to detect the problem. Yes, so we can also use S-flow records, but as you mentioned in the question itself, so the S-flow records kind of samples the traffic. So the NetFlow kind of provides us the entire volume of how much the traffic is being sent and stuff. So here we are using that to get more accurate information on the entire volume to kind of narrow down further. So that is the reason we were using NetFlow here to figure out the actual affected flow, and then we were moving forward with other troubleshooting steps. I hope this answered your questions, Ron. Thanks.
Thank you, Vignesh. Okay, so if there are no other questions, then we'll wrap it up. Thank you everyone for joining us today. Looking forward to see you on the next session. Have a great day, everyone.